Good morning to all. I'm Dr. S. Janardhana Rao. Series of lectures we are discussing about operating systems and different concepts we covered. Today I'm going to cover disk scheduling. Already in my previous lecture session, I explained some concepts and one or two disk scheduling. So disk scheduling means first of all, whenever you want to save the file or any document, so the OS will check the size of the file and available memory, and that it will check it. So in this one, after saving the file, you want to retrieve or you want to read back. So in that case, the OS will where it is saved, where it has saved, in which disks it is saved, which tracks it is saved. Again, that CD should be brought under the arm, that read and write head. So here, we have seen in the previous session, this one, we have seen that SSTF is a SSTF shortest seek time first algorithm. Select the disk IO request, which requests the least disk arm movement from its current position regardless of the direction. It reduces the total seek time as compared to FCFS. It allows the head to move the closest track in the service queue. So here, just if you look at this one, so actually initially the head at 58 track, or you can say 58 cylinder. So for the completion of the program or completion of execution, it requires these are the tracks to be structured. These are CDs. These are the cylinders to be moved. I mean, you have to cover. You have to read it from there. So 45, 21, 67, 94, 89, 52, 61, 87, 25. So in this case, shortest seek time, SSTF. So what it does, so in this one, available, what are the, from these, your head is at 50. So out of this, all these cylinders, which is near to the, out of all this one, which one is near? So that is 45 is near. So it is given the 45 the first question, but even 45 in between also, it touches that. First it goes to where it is nearby to 50, 45. So after that it is 52. So 45 is near, 52 is nearby 45. So like this, with the shortest time, it will reach the track. That is the shortest seek time. So like this, we have discussed it, and now next scheduling algorithm is scan algorithm. The scan algorithm is like this. It is also called a elevator algorithm. In this algorithm, the disk moves into a particular direction till the end, satisfying all the requests coming in its path, and then it turns back, moves in the reverse direction, satisfying the request from coming in its path. So we will see the example. It works in the way an elevator works. Elevator moves in a direction completely till the last floor of the direction and turns back. So if you look this one, if you look at the example, we consider the following disk requirement, disk sequence for a disk with the 100 tracks. So 98, 137, 122, 183, 14, 133, 65, 78. These are the tracks on the disk. So this one, head pointer starting at 54 and moving in left direction, and number of head movements in a cylinder using the scan schedule. So initially at 54, so it will go to the extreme end. So extreme end is 0. So from 54 it goes to 0. On the way, 14 is one of the cylinder given in this sequence. So it goes to 14 and goes to 0. From 0 again it reverses back from there. It means extreme end. It touches the extreme end. So 183 is XTML. So it will go from 0 to 183. And the way, what are the cylinders available? It will touch all these tracks and comes to the extreme end. So this is a scan. So if you look at, this is a, you have to remember it. So going to end and coming to beginning. Okay. So next we will see another one, another scan. We will see that is C-scan algorithm. C-scan means the arm of the disk moves in a particular direction, serving requests until it reaches the last cylinder. Then it jumps to the last cylinder of the opposite direction without serving any request. Then it turns back and starting moving in that direction, serving the remaining request. So we'll see what is the difference between scan and C-scan. So if you look at this one, just see like this. Consider the following disk requirement: request sequence for disk with 100 tracks starting 98, 137, 122, 183, 14, 133, 65, 78. So head pointer starting at 54 and moving in left direction. Find the number of head movements in a cylinder using C-scan scheduling. So in this one, if you look at this one, starting at 54 and go last, in the reverse it will jump here straight away to the last, but it won't serve any tracks. It won't serve anything. It won't touch. So now from coming here, it will start serving the request tracks. This is the only difference between the scan and C-scan. So this is in the scan, it used to serve in this direction also, but whereas it won't serve in this C-scan. This is the only difference. So as to know, you know how to calculate this one. This is a difference from starting to reaching one. So if you add all these things, you will get 387 cylinders. That's this is the only difference between the scan and C-scan. You don't find serving in the reverse direction. It jumps to the end, and from end it starts serving the. So this is only difference between the scan and C-scan. So next one, this already we have seen. C-scan provides more information rate time than scan. The head moves from one end to disk to the other, serving request as it goes. So it jumps back from here. It jumps back like this in one direction. Go back to last. In this direction, it won't serve anything. So only one direction only it serves. So another one is C-look. C-look version of it is also another type of model. You can say that C-look version of C-scan only goes as far as the last request in which. So what is the difference between the C-scan and the C-look? But both are different. But in the C-scan, it used to go last one. From there it jumps back. Whereas it goes only the available. It won't go last. That is the only difference. It starts jumping from itself. It won't go last. This is the last. This is the last. It won't go till that one. It jumps from here. This is only difference between C-look and C-scan. Rest all same. It won't in reverse. It won't serve, but it won't go last tracker like last cylinder. That is only difference. It won't go last. It starts only whatever the least or maximum track. It will go up to there and it will jump from there. It's the only difference between C-scan and the C-look. So it is like a scan scheduling algorithm. To some extent, expect the difference that in this scheduling algorithm, the arm of the disk starts moving inwards or outwards when no more request in that direction exists. So the algorithm tries to overcome the overhead of scan algorithm which forces disk arm to move in one direction till the end of the end, regardless of knowing if any request exists in the direction or not. So we will see, look, this is a look algorithm. So if you calculate the cylinders, number of cylinders crossed, so it is less. If you look at this one, it won't go till the end. This is only the difference between the scan and look. So disk management, low level formatting or physical formatting, dividing the disk into sectors that the disk controller can read and write. So, and to use a disk to hold files, the operating system still needs to record its own data structure on the disk. Partition the disk into one or more groups of cylinders, and logical formatting are making a file system, and bootlock initialization system F, and the bootstrap is stored in the ROM, bootstrap loader program, and methods such as sector separating used to handle bad blocks. Disk management. So disk formatting. A new magnetic disk is blank state. It is usually a flatter of magnetic recording material. Before a disk can store data, it must be divided into sectors that the disk controller can read and write. So this process is called low-level formatting or physical formatting. Low-level formatting fills that. So it means that, so this is our disk. So over this, some material is coated on this one. So this is tracks, and these are the tracks, and these are the sectors. So over this one, some magnetic material is coated. Whenever you want to save data on this, so whenever one is to be saved, so there will be, they will put one data dot, that is arrow. That means it is one is saved there. Like this, the data will be saved on the tracks. So in this formatting means the complete depolarize, the material will be depolarized. So before a disk can store data, it must be divided into sectors that the disk controller can read and write. This process is called low-level formatting or physical formatting. So the low-level formatting fills the disk with a special data structure for each sector. So what I want to say, whenever any file is saved, so in the sector itself, or in the, suppose this is our hard disk. So some file is saved here. So automatically we will make a data structure here, and our order files saved in the structure. It will make the data structures. So this is a root data structure. This is root from here. The files will be saving here. So that will also be included in the directory structure. Some place is allotted for this one in the hard disk itself. So whenever any file is saved, in this directory will be updated automatically like this. So this structure will be available in the hard disk itself below the drive. So whenever any file is removed or deleted, automatically data structure will get updated, removing that file from the directory. So like this, we have to assume. So what is happening in the disk or disk? So the data structure for a sector typically consists of a header, a data area, and a trailer. So the header and trailer contains information used by the disk controller, such as sector number and error correcting code, etc. So this is how disk is maintained. So when the controller writes a sector of data during I/O, the ECC is updated with a value calculated from all the bytes in the data area. When the sector is read, the ECC is recalculated and compared with the stored value. So in this one, you have to understand one thing. Whenever you want to save any file, so file, you are writing a program here, you want to save this file. So this is your hard disk, C drive, D drive. So if you just give the name of this file, the OS will ask, what is the name of the file? So when you are writing some xyz.c, This will be converted to a number. That is by ASCII code. This for each character there will be one equivalent ASCII code will be there, and the ASCII code will be added and we'll get the unique number. That is the file number. Once the file is saved here, and in this directory, the directory it is like this. Directory structure will be there, and in this directory structure, that number will be there. That number, file number, some HX will be there, and along the HX, that where physically data is saved, that number also saved, that address also saved, some XX. So this is included in the directory. So whenever you want to open the file again, it will be converted into that file. Will I switch on or take the cursor over the file name, and when you click on the file name, automatically that file name will be converted into a number. Then it will carry on the search in the directory structure. Where is that file available? So once the file is available, next to that number, that address will be there. So that address will be fed into the program counter of the CPU. That is logical address. So if the stored and the calculated number are different, this much indicates that data area of the sector has become corrupted, and that the disk sector may be bad. The ECC is an error correcting code because of it contains enough information that if only few bits of data have been corrupted, the controller can identify which bits have changed and can calculate that what other correct value should be. So in these reports, a recoverable software error, controller automatically does the ECC processing whenever a sector is read or written. Boot black. So computer ROM contains a bootstrap program OS integrated with just enough code to find the first sector on the first hard drive and the first controller. So load the sector into memory and transfer control over to it. The first sector on the hard drive is known as the master boot record (MBR) and contains a very small amount of code in addition to the partition table. The partition table document shows how the disk is partitioned into logical disks and indicative, especially when the partition is active or boot partition. The boot program then looks at the active partition to find a operating system, possibly loading up to slightly larger, more advanced boot program along the way. A double boot or a larger multi-boot system, the user may be given choice of which operating system to boot when a default action to be taken in the event of no response with some time frame. So this is a partitions automatically be done whenever we switch on the system. Your partition 1, partition 2, partition 3, partition 4. So partition table, boot code. So that will be uploaded from the ROM to your system hard disk. So bad blocks. What is bad block? Bad block means no disk can be manufactured to 100% perfection, and all physical objects wear over time. So for this reason, all disks are shipped with a few bad blocks, and additional blocks can be expected to go bad slowly over time. Modern disk controllers make much better use of the error correcting codes so that the bad blocks can be detected earlier and the data is well recovered. If the data on a bad block cannot be recovered, then hard drive or error has occurred, which requires replacing files from backups or rebuilding them from scratch. So it means that in the memory, in the hard disk, maybe some memory block may be corrupted. So that is we call our OS having the self-healing power. So whenever any bad blocks are there, so whatever data available at these bad blocks, that can be recovered back and put position into some other blocks. So that what's bad blocks and detected by the OS. Swap space management. In this modern system, typically swap out pages as needed rather than swapping out entire processes, and the swapping system is part of your virtual memory management system. So managing swap space is actually obviously an important task for modern OSs. Swap space use. The amount of swap space needed by an OS varies greatly according to how it is used. Some systems require an amount equal to the physical memory, physical RAM. Some want a multiple that. Some want the amount equal to the amount by which the virtual memory exceeds the physical RAM. And some systems use little or none of all. Some systems support multiple swap spaces and separate this in order to speed up the virtual memory system. So swap space location. So swap space can be physically located in one or two locations. As a large file which is part of the regular file system, this is easy to implement but inefficient. Caching the block location helps in finding the physical blocks, but it is not a complete fix. As a raw partition, possibly on a separator or a little used disk, was more control over swap space management, which is usually faster and more efficient. The downside of the keeping swap space on a raw partition, that is, it can only grow by repartitioning the hard drive. So we'll continue the concept in the next session.
Like, share and subscribe. Hit the bell icon for more updates.